The biggest surprise about skyhooks is not the physics, it is the traffic problem. A long tether in low Earth orbit is not just a vehicle. It is a moving piece of infrastructure that sweeps through a huge volume of space. That swept volume turns routine spaceflight into something closer to air traffic control. If you cannot manage conjunction risk at scale, you cannot operate the tether, even if the engineering works. Start with the basic premise. Rockets spend most of their mass on propellant. Skyhooks, momentum exchange tethers, and electrodynamic tethers try to shift that burden. They move energy and momentum into reusable equipment already in orbit. Instead of throwing fuel away on every launch, you build an orbital machine. Over time, you reuse it, again and again. That idea is physics permitted. It is also not operating as routine service today. As of 2026, there is no operational orbital skyhook, and no non-rocket Earth-to-orbit system offering regular launches. Chemical rockets still set the baseline, and reusable heavy lift sets the cost floor that every alternative must beat. So what is real, right now, and what is still mostly paper? One solid area is analysis of electrodynamic tethers. An electrodynamic tether is a long conductive line interacting with Earth's magnetic field. In simple terms, it can trade electrical and orbital energy. With the right control and power setup, it can change a satellite's orbit without traditional propellant. Published work has put this on a firmer dynamics and control footing. That matters, because it reframes tethers as a kind of in-space electric propulsion by infrastructure, not just science fiction elevators. Yet even here, the gap is obvious. Modeling a maneuver is not the same as operating a service. Operational service needs repeatability, fault handling, and safe procedures under real conditions. It also needs verification that the tether can survive the environment and not become a hazard. That leads to the second major finding. For tethers, debris is not a side issue. Debris is the core design constraint. Low Earth orbit already contains a population of objects large and small. Some are tracked well, many are not. A compact satellite can sometimes maneuver or accept risk within a relatively narrow corridor. A long tether is different. It presents a large target, and it crosses many potential intersection points. Any severance event is not just a single failure. It can become a debris creation event, with downstream effects for other operators. There is a reason debris research remains central to this entire topic. Collision risk in LEO is systemic. It is not just about protecting one asset. It's about preventing cascades of collisions that degrade the environment for everyone. For senior leaders, that means the most important material in a tether business case may be governance capacity, not carbon fiber or nanotubes. A third insight is about sensing and navigation. Skyhooks and momentum exchange concepts depend on timing and proximity operations. That is where the evidence base is quietly strong and quietly limiting. Researchers have studied optical co-orbital measurement, meaning optical methods to observe objects that share similar orbits. There is also detailed work on initial orbit determination from short observation arcs, including cases like CubeSats, where tracking can be sparse. These topics sound abstract, but they control whether a spacecraft can rendezvous reliably, whether inspections can be done safely, and whether a capture and release sequence can happen on schedule. If your system requires two objects to meet at the right place and time, small errors can become mission failures. For a momentum exchange tether, a missed rendezvous is not a minor inconvenience. It can be a major operational disruption, because the tether's rotation, attitude, and schedule all couple together. In other words, the business case hinges on state estimation, not just on mechanical strength. Now add the fourth finding, which is more strategic than technical. Non-rocket launch is not one market. It is at least three different investment categories with very different risk gates. First, there are electrodynamic tether services. These aim at orbit adjustment, orbital boosting, and potentially deorbit support. They can be valuable even if rockets remain dominant, because they target in-orbit propellant savings. Second, there are momentum exchange tethers for in-space transfer. Think of them as orbital machines that exchange momentum with payloads, reducing the propellant needed for certain transfers. Third, there's the most ambitious idea, true Earth-to-orbit replacement, where payloads are picked up and thrown into orbit with minimal onboard propellant. Those are not interchangeable. They demand different demonstrations, different regulation, and different insurance treatment. A leader who funds them as if they were a single program risks buying confusion instead of capability. A fifth finding concerns comparisons. Any tether proposal needs to be compared against conventional orbital maneuver baselines. We already have well-characterized propulsive transfers, like LEO to GEO, that set expectations for delta V, time, and reliability. A tether system has to do better on some combination of cost, cadence, or mission flexibility, while also satisfying safety constraints. And here is the uncomfortable truth. Reusable rockets are not standing still. They set a moving benchmark. So tethers do not get credit for being different. They only get credit for beating the best alternative on a specific mission class. That pushes strategy toward a very particular kind of near-term posture. The most credible work, from a capital allocation view, is enabling technology with independent value. Invest in better relative measurement. Invest in orbit determination that works under short, imperfect tracking windows. Invest in debris environment modeling, and in orbital capacity methods that can support licensing decisions. Fund tether dynamics validation, because control authority and stability are where concepts go to die. Those investments pay off even if a full skyhook never happens. They also make the space economy more manageable in general. Better tracking and governance support every operator, not just tether dreamers. Governance itself is not a footnote. Licensing categories for long, swept volume structures need to exist before someone tries to deploy one in anger. Rules must cover conjunction reporting, autonomous safing behavior, disposal obligations, and third-party collision exposure. Without that, you are not just risking your own asset. You are shifting risk onto everyone else in the orbital shell. That is why insurers and underwriters matter here. A long tether concentrates unusual risks: severance risk, collision exposure across a large area, operational interruptions from conjunction warnings, even strategic interference, because a tether can be seen as infrastructure that affects orbital lanes. If risk cannot be priced, the project cannot be financed at scale. When you step back, the timeline becomes clearer. From 2026 to 2050, expect modeling, subsystem demos, navigation work, and electrodynamic tether experiments. Niche services are plausible, especially ones that help with deorbiting or station keeping. Routine skyhook pickup from Earth is not established by the evidence. From 2050 to 2100, limited operational tether services become plausible if control, survivability, tracking, and licensing mature together. Notice the word together. Progress in only one area does not unlock the system. Strong materials without governance still fail. Great governance without reliable control still fails. Beyond that, larger momentum exchange infrastructure could become part of broader cislunar logistics. It could support manufacturing in space, satellite servicing, and engineered transit corridors. But those are contingent futures, not inevitable ones. The physics allows it. The forecast remains weak until the messy operational stack is proven. So what should a serious decision maker ask right now? First, what problem are you actually buying? Is it cheaper surface launch, in-space transfer, deorbit support, station keeping, or orbital capacity management? Second, would your risk policy permit a long swept volume asset in a congested shell? And what threshold forces shutdown? Third, what evidence gate moves you from modeling to hardware? Dynamics validation, measurement performance, orbit determination, debris capacity approval, or insurance pricing. If you remember only one line, make it this: skyhooks do not fail first on physics. They fail first on operations in a crowded sky.